Hello, everyone. In this video, we're going to start our notes covering section 2.7 on derivatives of functions given implicitly. So to get started on this section, we have our preliminary example. So in this example, we're asked to consider the circle defined by x squared plus y squared equals 25, whose graph is given on the right. We need to find a formula for the derivative of y with respect to x without solving for y first. So before getting into this, let's take a look at this graph. So we could look at this graph and ask, is this graph a function? So you might have seen a way to check for whether or not a graph is a function is if it passes what's called a vertical line test. So that test says that if there's only one place where our graph touches a vertical line, then the graph is a function. And now that statement is a little vague. Is this graph a function? So when we ask, is a graph a function, we mean, is it a function of x? Is it a function of the input? So in this case, this graph is not a function of x because there are two outputs for one x input. However, this graph is still a function of some implicit, say, t variable going on or controlling both x and y. So that's not too important. What's important is that we still can take derivatives of graphs like this, or equations like this, where y is not isolated. So what we've been seeing so far are just functions like y equals x squared plus 25. But we've never been in this situation where y is within the equation that we're looking at. So when we're dealing with a function like the one given here, or the equation given here, we can see this graph as being two functions of x put together. So we have one function on this upper hemisphere, so the positive values of y, and then the negative values of y. So we could see this graph as being two functions of x, where again, one case the outputs are positive, one case the outputs are negative. But regardless, we can still talk about how this graph changes. So if we look at a point, we still have a tangent line here. And at this point, maybe on the negative sign, we still have a tangent line. So we still can compute things like the derivative of y with respect to x. And so how do we do that when we're given an equation defined implicitly? So this equation here, or this function, is called an implicitly defined function. And it's implicit because we should think of both x and y as being functions of t, some parameter. If you're taking a physics class, you'll see more of these types of functions. You've probably seen these maybe somewhere in your math history. If not, that's completely okay. We're going to work through these examples together. All right, so let's get started. Our goal is to find dy dx. So this means that we want to treat this graph as being a function of x. So it's going to be different. We're going to have different derivatives or tangent lines for different outputs, like the y output up here or here, but we're still going to be able to compute how y changes with respect to x. All right, so let's go ahead and do this. So first, I'm just going to rewrite my equation, x squared plus y squared equals 25. So because I want to know how y changes with respect to x, I should think of y here as a function of x. So I'm going to make that super clear by writing f of x for y. I'm going to write that down. So I'm going to say let y equal f of x so that we remember that y is a function of x. In other words, y varies with respect to x. And that's the whole point here. We want to know how y varies with respect to x. Okay, so now what we need to do is take the derivative of both sides. So let's go ahead and do that. So taking the derivative of the left-hand side, I'll just write it out so we can see all of the steps in their glory. All right, so that left-hand side, we just have a sum going on. So we're going to compute the derivative of each term. So the derivative of that first term here is just the derivative of x squared with respect to x. So we're just going to use the power rule there. I'll write that out, power rule. And then now when we take the derivative of this next term, we should recognize this as a composition. So we're going to need to use the chain rule. The inside function is f of x. The outside function is squaring. So if we want to use u's, we could let this be u. So the derivative then becomes 2 f of x using the power rule. The 2 comes down and 2 subtracting from that exponent. And we just leave u here. And maybe I'll even put 1 in the exponent so it's clear I'm using the power rule, times the derivative of the inside function. So times the derivative of f of x. And now what is that equal to? Derivative of 25, derivative of a constant is just 0. All right. So now we can substitute back in y for f of x. So then this becomes, and I'll write that out here. So sub back in y for f of x. So that becomes 2x plus 2y times dy dx equals 0. So now our goal is to solve or find dy dx. So we're almost there, but we just need to isolate dy dx. Isolate or solve for dy dx. So we can do that with just a little bit of algebra. So what we're going to do is subtract 2x from both sides to try to get this dy dx by itself on one side. So now that first term goes away. So we're left with 2y dy dx equals negative 2x. And now we're going to divide both sides by 2y to cancel out that term multiplying by dy dx on that left-hand side. So now that just becomes dy dx is equal to negative 2x over y. There's an extra 2 on that denominator there. So then when we simplify, we just get negative x over y. So then I can just remove that middle part and I have dy dx equals negative x over y. Now I just want to make a couple of comments here, and feel free to pause the video and rewatch the progression of computing that derivative so that you're really comfortable with the solution here. All right, so now I just want to make a couple comments. I want to actually compute this dy dx at a couple of points. So notice, first of all, that dy dx has both x and y in it. I'm just going to write that down because it's an important observation. Dy dx is defined with both x and y. So why is that interesting? Well, let's consider a point on our graph. So here's a point. Looks like -2, up 1, 2, 3, 4, and a little bit, maybe 4.5. So this point here on our curve is -2, 4.25. So that's our point here. We also have a point here that's at -2, down -4.25. So if we want to know the derivative at either of these points, then we need to use both x and y, both of these coordinates, to find the dy dx there, or find the slope of the derivative. So I'll just say this means, this is just an example. This means at the point, we'll use the positive one, -2, or the positive output here, at -2, I'll zoom out so you can see, comma 4.25. the derivative is negative 2 over 4.25, which becomes something like about 1/2. So the slope here is about 1/2. And notice that if we do this with the point on the bottom here, well, the negatives, when we do that fraction, x over y, are going to cancel out and we'll be left with a negative slope. We can see that that should make sense. We're going to actually get the same number because we'll use that same quotient, 2 over 4.25, but now we'll have negative. Awesome. Great work working through this first example, everyone. Again, please rewatch any parts of this video to help make this new concept a bit more familiar. And I'll meet you at the next one.